from Linaro Hisiilicon 19 team. Today we're discussing about a common accelerator framework, Warpdrive. First, the agenda. First, let's talk about some background. Then provide our target, what we want to do, and then let's do some investigation. Finally, we provide our solution, Warpdrive, and give some performance data. The background, currently more and more hardware accelerator appears in the market, like decompressor, compressor, and the encryptor, decryptor appears on the market. So the accelerator will be more and more popular. Also, AI is very hot. We all know AI needs some matrix computation, so it needs long time. If we can use hardware accelerator, it will give a better performance. So we want to, but in order to get a better performance, most of them use to be used in the user space, just like a DPDK. And we need a software infrastructure to support this application. This is especially important in ARM because ARM can be customized. Here is a general platform. We can see on the root complex, there is some no-iommu, there is maybe 3 types of devices. For some legacy devices, it cannot support SVA feature. About SVA is a shared virtual address we were discussing in the later. Also, some discrete devices is attached by the PCIe. And some integrated devices like graphics and accelerator. This is a realization in Kunpeng 920. In our realization, we just, it is integrated devices. It appears a PCIe, but in fact, it is on Amba bus. We can see in the later, it is just use zip and gzip as an example. Above this accelerator, there is a queue management. It can provide 1024 queues. Each queue can support one process. It means it can, there is 1024 processes can run in the same time. So only one accelerator can support 1024 processes running together. So what we want to do? What we want first? It is we want to use a user application to directly call this accelerator to get a better performance like DPDK. And then we want to support multi-process since it supports 1024 queues. It can, the 1024 process can run together. Then also virtualization is very important. Currently we use SRIOV. In Kunpeng 920, we support 1PF and 63 VF. They can just share these 1024 queues. We support not only zip and gzip, we also support HIPAA, SM34, PoE, SEC, this accelerator. So it includes a lot. This is what we want to do. Then let's investigate how to do this. First is in some cases there is our no-iommu is not ready. So first case is no-iommu. In no-iommu, it is very simple. The device have to allocate a physically continuous memory via the DMA allocate coherent. Then we map to the user space. Since we focus on user space application via the DMA and map coherent. But the limitation is very, there are 2 limitations. First, we need physically continuous memory. Second, we may reserve some memory using CMA like that. Second, we use no-iommu. No-iommu is very good. It can provide some protection since no-iommu can do some isolation. Using no-iommu, we do not need physically continuous memory since no-iommu can translate the OVA to the PA. So no need physically continuous memory. But there is still one limitation. Currently, in server area, the virtualization is very popular. We just do the common feature. We use the VFIO feature to support the virtualization. In the virtual machine, they also want to access the device. There has the RVA. If this RVA is in user space, though it is in virtual machine, but it is in user space. But currently the RVA is in the kernel space. They may have conflict. In fact, they may have the same RVA, but in a different area. Now, how to solve this problem? Currently, we just using the no-iommu domain unmanaged. It just alloc a new domain, a new page table to be specifically used by the virtual machine. But if we use this method, the DMA API cannot be used, since the DMA API is used by the kernel. So when we want to switch back. We just use the default our domain. This is our domain, our MMU feature. Then next is SVA feature. SVA feature is a new feature. What SVA means the shared virtual address. Some MMU architecture just call this shared SVM, shared virtual memory. That's the same meaning. The SVA feature is very cool. It just copy the page table from the MMU. So although our MMU and MMU, they share the same page table, so they can recognize each other. Also, what's more, the more important is it supports the device page fault. So user can directly malloc a buffer and then directly use this buffer to the device. The device, if the device finds there's a page fault, and then the trigger interrupt to access to malloc memory. So this is very cool. Since in the whole system there is a unified page table. Also, we can support multi-process, so it just meets our requirement. Since each process can be distinguished by the PSID, just the process ID. And now kernel DMA API can be used in the meantime with the user space API. Since for the kernel we just use index 0. Here is example. Here is a short explanation. For the CD tables, you can see the CD table 0 is specifically used by the kernel, and the user space use other page table that indexed with different SSID. SSID means the substream ID, just PSID in the PCIe space. We can see the SSV. SSV is a signal. When SSV is 0, this page table is used by kernel. When SSV equals 1, it is used by the user space. Usually, the SSV is controlled by the silicon or hardware, so they can run it together. For example, if for the we have some DMA for the control, then we use it handled in the kernel. Using the kernel DMA. So at that time, SSV is equals 0. In the meantime, there is SSV equals 1. We can doing the user space DMA. So they can working together, no conflict. It is, and here is a non-path. First, SID. SID is a using stream ID, it can identify different devices. For example, we have 5 accelerators. Each accelerator has a different SID. We can using SID to identify device. Using SID, we find the entry in the stream table. Then the different process. Only the one per accelerator. Using in a different process, how to distinguish them. There we use SSID. SSID is a substream ID. Just in the PCIe, we call this is a PSID. But the purpose is to identify the different process. Now using with the help of SID, we can translate RVA to the IPA. This SVA native labeling on ARM is now working by the Jing who is from ARM. This table is just stage 1. Currently, stage 2 in the kernel still not supported. So here, just give some example. Then currently, we give out Warpdriver. It's our solution. Warpdrive is accelerator framework. It's especially focused on user space. It is proposed by Kenneth from Hisilicon. It includes both kernel space and user space. In kernel space, there is a USCCE. USCCE is a framework. Like the meaning is user space accelerator framework. And also, there is some user space facility like Warpdrive library. And it's totally based on the no-iommu feature. Since no-iommu is very, very safe, it can do some protection since there is some isolation. Based on our investigation, we think the no-iommu SVA feature is very cool. So we especially use this no-iommu SVA feature. It can maintain a unified address space between a process and the device and the hardware context. Of course, multi-queue and multi-process should be supported. For some platforms, the no-iommu is not ready. In fact, no-iommu still working. SVA feature is still working now. So we give some compatibility. We support no-iommu. We support no-iommu has no SVA feature. But our final target is support SVA because it's very beautiful. Virtualization is also supported. Currently we use SRLV feature. We're using VFIO PCI to support a virtual machine. Here is a big map of Warpdrive. You can see in the layer there is many applications. We support many applications, even for the one accelerator. They can run in together. Each application, they just request queue, just get queue from this library. Under the library, there is a USCCE framework. The USCCE framework registers to the system via the CHRDEV interface. Also, it's using this interface to provide some information, like what accelerator it is, how many queues still exist in the system, and other feature. Like later, it is queue management. Queue management is a helper. We support, in our plan, we support zip, gzip, hyper, SM34, SEC, PoE. This accelerator is all in our plan. This part is specifically the Warpdrive. In the meantime, it can be registered to the crypto. Crypto is a kernel already, there is a crypto framework. They can work together, no conflict. So the existing application still can using crypto. But our Warpdrive framework is specifically focused on the user space to get a better performance. Warpdrive kernel, currently, Canis sent version 3 last year, November, to get some comments. In the meantime, we do some development for our internal products. We support no-iommu, non-SVA, SVA capable. It can be all supported. Jin is also working on the SVA feature. His main target is doing the upstream. They also co-work with Intel. And Jin, we are working closely with Jin. His patch has been verified on our framework, and we also give him some feedback. Currently, we support zip, gzip, and hyper accelerator. In our plan, our colleagues is now supporting SEC, PoE, SM3 and 4. It is maybe released later, several months later. The user space currently multi-queue is supported, and also it supports async mode. You can batch processing. You can send several commands and trigger to run together to get a better performance. But for the user space, our two main targets. The first main target is we want to support OpenSSL. OpenSSL is very important because many accelerators now using the OpenSSL interface. So it's our first priority. We want to, second is we also adapt to the zlib. We will provide some patches. When the system finds there is a hardware accelerator, it can switch to our solution. And if there is no hardware acceleration, it just switches to the default zlib. Currently, there is some challenge. The most challenge is gene patch. Gene patch, in fact, it process a long time. Some discussion. It's not an easy task. He's doing now, and he needs some help. And also, the SVA only sharing the stage 1, and it does not support stage 2 now. Also, the SVA feature, I just find it support PF and do not consider VF. But only in this connect, we get some news. The Eric from Intel and Jogby from Eric from Red Hat, they have some patch set to support the virtualization. I'm just verifying this feature. So A and B is both A and B is supporting the virtualization. If their patch set is supporting virtualization, then the A and B challenge is disappearing. Then later, our accelerator is not a real PCI device. It is fake. It appears like PCIe, but in fact it is on AMBA bus. So we need some quarks. Currently, we have sent some patch to the kernel to do some the quarks since what we use is using the SMU store feature, but the SMU spec disallow the PCIe device to use this store feature. Since the PCIe, it can support the device patch fault. If the PCIe using the SMU store feature, there will be conflict. So the spec disallow the PCIe device to use this store feature. But our accelerator is the integrated device. It is a fake PCIe. So we need some quark. We have sent some patch to the kernel. And then the performance, I simply do some performance. We can see the first layer is CPU behavior. And the right side is 3 types, no-iommu, iommu, non-SVA, and ioMMU SVA. We can see the hardware accelerator can get 100 or 200 times compared with the CPU speed. And this is the performance from the Hisilicon product team. It supports, since it is in the product team, they want to be stable. Currently, the SVA feature still not be upstreamed. So in this performance test, we're using the no-iommu feature. Left is IC algorithm. Right is DH algorithm. We can see the upper layer is only software. The lower layer is using hardware accelerator, using OpenSSL interface and the Hyper accelerator. We can see when we use software methods, the CPU usage is always 100%. And when we use a hardware accelerator, the CPU is downgraded a lot. You can see only 1 point, and the CPU usage improved a lot. And the speed is comparable. Can you see? Sorry. Okay. It has.
My glasses on.
This performance data is from our product team, but they can be accessed. Currently, we have put our code, both the kernel code and the user space code, to the GitHub. Everybody can get access, and we very welcome many companies to join together. Let's get this accelerator framework to be mature and used by many companies. If there's time, we can do a simple demo. We have upstreamed the code. Even you have no real hardware, we provide some QEMU to assimilate. Then it is very much QEMU. If you know hardware, it can be also test. accumulate. This is the cumulative test. It is very simple. The cumulative driver, the dummy, just using a dummy driver to.
The cumulative doesn't provide a hardware acceleration.
Yeah, no hardware. The cumulative, if you have currently this, we're using the D05 or D06. But if you have no hardware, you can using Cumul. Everybody can download this code, have run. It's very simple. Cumul, everybody can use that. You can verify the framework. If you have some feature, user space also can be verified.
But it doesn't support the SVA, right? The QEMU don't support the SVA, IOMMU, this kind of feature don't support. Just to verify the framework, this software feature.
Yeah, verify. So. And this is the real hardware. I just connected to the hardware lab. I'm doing the stress test overnight, and first is the CPU. CPU, you can see the time is costed almost 2 seconds. I run 10 times. And then we just using our. This is using hardware. You can see it's just 100.
We can't see it. Too small.
好，这怎么放大 ？You know?
Okay, we trust you.
Yeah, we trust you.
能放大吗？啊，就这样放大了。
行吗？
啊。This is first we running the software. Software gzip. It costs 2 seconds. This is a hardware accelerator, 100, right? 100 times faster. So I'm doing the also. You can running. Okay, some issue. It can support multi-queue and it can support async mode. So that's it. Any problem? We really want to welcome other companies to join us together to make this framework mature. And if you have any question, is also here.
It's being said it's a general framework for. It's being said it's a general framework for hardware acceleration, but it seems like it only covers application like compression and crypto. I'm not sure how general it will be to cover more subsystem or just application like compression and crypto.
Yeah, even the AI engine you can also use. Internally, we also consider to put in our AI engine to this framework.
Okay.
Quite general.
Okay. So even for some outstanding subsystem like networking, because so right now Linux kernel have a heavy network stack, which Intel introduced a DBDK and something like that too.
From the very beginning, we cooperate with the LNG in Linaro, but finally ODP project is not precise, so it's not there. But actually, from the beginning, the requirement is considered.
Okay. So it sounds like it's the direction to cover more and more subsystem too.
Yeah, the basic idea is if you want to export the hardware to the user space, you have to protect the kernel from maybe go around the hardware and attack the memory inside the kernel. So you need protection between the kernel side and the user space side. Right. So SVA is necessary.
Okay.
In those cases.
So it sounds like SVA only handles. I guess it's only handles the memory aspect. What about interrupt? I think for hardware acceleration, both memory and memory access and interrupt handling will be.
Yeah, but
handled.
most cases you will need a pooling style interface, right? You send a lot of requests to the hardware, and then you may waiting on some file. We give a pooling interface there, and then if the hardware finish some loop, and then he give a signal in the kernel, and then you can direct free the thread and continue the manipulator to the data package.
Yeah, that's probably something we can do around that. There are ways to route, to proxy interrupts to user space so that you don't have to poll on some queues. That would certainly save power instead of just polling on your queue to wait for the data to be returned.
Yes.
Okay.
Aren't there already, like, for example, socket-based interfaces that handle this today?
Yeah, if you want to go through the whole network layer or use netlink sockets, I mean, there's a wide range of interfaces at the kernel level that we can use for that. But we have things like event FDs, RQFDs that are designed for that.
Because the issue that I see there is that any such accelerator framework is only as good as it gets used by actual applications. And the more generic and standard that interface is, the easier it is going to be to enable tools such as gzip that will actually get shipped by the Linux distributions to enable such features when they can actually be used everywhere.
So that's indeed one of my worries, is that that effectively creates user space ABI, whether you want it or not. So by giving direct access to an accelerator, indeed you get a lot of performance. The drawback is everybody will have a slightly different gzip engine with a slightly different interface. If we want this to be successful, it needs to be universally adopted as the only possible implementation ever of an accelerator. That's going to be difficult to ensure.
Yeah. So that's why we are here and try to ask everybody to join, and we can find out. Maybe we have several companies have a small group first, and then slowly people add to it, and then it will become a general framework.
Yeah, I think one of the effort that needs to be engaged is standardization. This can only be successful if it's standardized and everybody agrees that this is the recognized standard, because it effectively creates ABI.
Yeah.
User space has to know about the queue format and how things that get delivered. So either we use our usual mechanism, which is to use the kernel to abstract the way the hardware works, but we lose performance, or we go for maximum performance, but we absolutely need this to be completely standardized without any quirk. It needs to be absolutely perfect. Challenging.
Yeah. Yes. But anyway, the requirement is always there. Like QAT today, even for several years, they still run out of mainline kernel. That's because there's no way to prove it's safe, at least. They still use a no-iommu mode. But it's necessary because it's really very fast. People still use QAT framework without MMU protection. So I think the requirement is there. So I think it will be pushed forward.
So why not use create this new?
Yeah, VFIO should dedicate the whole device to the application.
Yeah.
But normally, as accelerator, you hope the accelerator can support many processes at the same time.
Okay.
That's why VFIO is not suitable for this purpose.
But why not to expand the VFIO framework?
We try from the very beginning, but VFIO already have a lot of burden to do so. The first RFC for Warpdrive, we do it on top of on top of VFIO. But finally, the community do not accept it. Yeah.
Okay.
I'm not sure right now if the Linux kernel, the subsystem like crypto and compression support hardware acceleration with some existing kernel user space interface or framework?
No user space. There is the crypto is just a kernel, just in kernel. No user space.
Actually, they do have user space interface.
Yeah, I mean, right now, without this general framework, application still needs to do some compression, decompression, or crypto stuff.
Yeah.
With some help.
But nobody use it.
Okay.
It's very slow.
Okay.
Because you need to go through a system control for every system call for any request.
Okay. I'm just curious how slow it is comparing.
Last year we have data. Maybe you can check from the network. We still have a slide for last year. We compare the user interface, the crypto user interface and our interface.
Okay.
I think more than 10 times.
Okay.
Yeah.
But for example, crypto has in the past been more widely adopted because it's possible to, to have like modules plug into an application such as OpenSSL, whereas zlib has been very much resistant to accelerators at this time, except for some forks by Google and some other forks. So it is not really about like the kernel user space interface that is the main thing that is blocking there, but rather the adoption by the user space applications.
Yeah, it's always a problem. But many customers do not care about that because they need performance. Right? It's still a lot community needed. People do not like it in general because it's not a general solution. But they always need performance.
I mean, we've got another talk now.
Oh, sorry.